Please.
I have a question about questions about water. Am I allowed to ask them?
Well, no, this is a great question. So, that is what Jessica's for.
Okay.
So, yeah,
But I
so.
want to answer. Oh. I didn't do
Okay,
homework,
this
so I
is a
got
great
that.
question as well.
She's a TA.
So Jessica's the TA. Yeah, that's right.
I did the homework after 9 o'clock, so.
Okay. Well, yeah, it's doing fine. Yeah, go see her. Yeah, and usually, it just depends on which one it is, but for sure she'll answer your question. Yeah. But I'm for sure able to answer it directly after class, or if it fits into something that we're talking about, right? So to maintain the continuity of the class. Okay. Yesterday we had introduced the exponential function. And again, at some point, I'll be sending you a link, or I'll put a link in the homework system to these notes, as useful as they might be or not be. We had defined e to be this, the unique number for which this is equal to 1. And so again, we were making the claim, I actually should keep the Desmos file up too, that what makes e special is that of all the functions, all the exponential functions that go through the point 0, 1, and they all do, whether it's 2 to the x or 3 to the x, let's put e to the x. I wonder, does it know e, or do I have to put, it does not know e. Oh, actually it does, e to the x. And then, or 3 to the x, that it is the base of e that has the property that the slope at this point is equal to 1. It's the only one that has this property. Okay. So that if I do y equals, what is that, x plus 1, that particular orange line looks identical to e to the x, right, and not the other two. That's the point. So that if I got rid of this one and this one, that's what makes e special. That is what makes e special. Okay. In the calculus sense. Now, in the pre-calculus sense, e is the base that comes out when you want to compound continuously. That's how e arises in the pre-calculus sense. But in the calculus sense, this is why we call it the natural base. This is why the inverse we call the natural logarithm, and so forth. Questions about that? So I envision, at worst, some bonus questions to just discuss why is e special? Why is e special? Right? I might ask something like that. Okay. In the calculus sense. All right. So now, having said that, we have this claim that we left, that the derivative of e to the x is e to the x. And oh my goodness, that implies something. So the claim is that the derivative of e to the x is e to the x. And so when I put this prime here, it means that when you take the derivative of this function, you get the same function back. Okay. Here's the proof. We're going to let f of x be equal to e to the x. The derivative of f of x is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. That's the definition. And yeah, every time, so let's talk about the game plan here. So we have introduced derivatives, talked about them in a general sense, and as we progress through, we're going to come up with rules. We already have the product rule, right? We're going to introduce the quotient rule. The homework is about the sum rule and a little bit of applications, right? But as we go along, we're just going to actually make pre-calculus worth it, in the sense that it was called pre-calculus because you talked about all these functions, and now we're going to go through every single one of those functions and ask how do they change, right? And so when we talk about the trig functions, right, so trig functions are important for a couple of reasons, but trig functions help solve any triangle, right? So trig functions find a relationship. Before trig functions, we had 6 properties about a triangle that we understood, and those were the 3 angles and the 3 sides, right? And in particular, for a right triangle, we knew that all the angles add up to 180, and we knew that for right triangles, how would you relate the sides? The Pythagorean theorem that a squared plus b squared equals c squared. But now when you ask the question, how are the sides and the angles related to each other, you can't do that without trig functions, right? That trig functions relate are the only functions that relate the sides of a triangle to the angles in some way, right? Fourier also showed in the early 1900s or the early 19th century that trig functions, that any wave can be written as the sum of sines and cosines. And so that whenever you're talking about a wave, you should be talking about sines and cosines, right? So trig functions serve that purpose. So you spend all this time in pre-calculus talking about all of that stuff in preparation for all of this stuff in calculus, right? So I'll say this just to say that that a large part of the class will be every time we introduce a function, it's a function that you've seen from pre-calculus, and we're going to be asking how does that thing change and what are the applications about it. Okay, so my point is that, well, one of my points is that this step here, we'll see this many times every time we introduce a new function and ask what is its derivative. We have to just go back to the definition. E to the f of x plus h is
e to the x
plus h, for sure. All right, so this is equal to the limit as h tends to 0 of e to the x plus h
minus e to the x
all over, perfect. We'll remark that e to the x plus h I can rewrite as e to the x times e to the h. Questions on that? Right, because you just add the powers when you multiply common basis. This is equal to the limit as h tends to 0 of e to the x times e to the h all over, perfect. We'll remark again that both of these have what in common? E to the x, and we'll factor it out. This is e to the x times
e to the h minus 1.
E to the h minus 1 all over h. This doesn't even depend on h, right? So that will stay. When h moves, that doesn't move at all. But oh my goodness, what is this? As h goes to 1, as h goes to 0, where does this go to? What is it? Okay, so 0 over 0 is never, so it's an indeterminate form, that's true, but we can't just stay at 0 over 0. Why? Because of the definition of D. That's exactly right. So on the previous page, we said that E was that unique number. That's what E is. Right? That's the definition. So this is equal to e to the x, so that this goes to 1 by definition. Yes?
How do you know it's 1?
That's a great question. So, and this is why it seems like cheating. So it's because we defined it that way. Okay, so I said a lot of stuff that you might have to say, well, wait, what are you talking about, right? So let's go back. So here, so I got a whole, oh, I don't know why I'm wasting my time. I got a whole family of exponential functions. So let's put some more, right? And I'm going to zoom out. And so there's 4 to the x, right? There is 1.5 to the x. I don't know if it's even going to like that. It does. Okay, great. There are tons of exponential functions that go through the point 0, 1, right? How many? Infinitely many, right? Now, they all go through 0, 1 at different slopes, right? And so if it is the case that the base changes, then the slope through this point is going to change, right? So in some sense, that's a function. Right? Is that okay? The other remark is that there is a base where the slope is 1. For some base, the slope is 1. Is that okay? Now, for that base, whatever it is, I'm calling it E. I'm going to call it E, whatever that number is. So E is the unique base whose slope through that point is 1, and it's given by the blue graph. Okay, so the blue graph is the 1, right? So that when I write, so whenever we define something, it's because it's there and we care about it, right? So E is the unique number with the slope at 0. Now, I haven't said this, but this is the slope at 0, right? It's e to the 0 plus h minus e to the 0 all over h, right? So this is the slope at 0, the instantaneous slope at 0, right? And so I know that for some number that's equal to 1, and I just happen to call that number e. Okay. So e is that number whose slope at 0 is equal to 1 for the exponentials, right? And so when I went and did this one here, all this is the limit of this thing, which we define to be 1. That's what's special about E. That's what makes it special, is that becomes 1. Now, if that were a 3, it would be something else. If that were a 12, it would be something else. Yeah.
I don't understand why the h at the bottom doesn't make it undefined because h approaches 0.
Say that again?
I know by definition that
Yeah.
becomes 1.
Yeah.
I just don't really understand how.
Oh, great. Absolutely. Thank you. So e to the h minus 1 all over h, right? And you're saying, look, we got some problems here because this goes to 0, yes? Is that what you're saying?
Yeah.
Excellent. Tell me about this. What does that go to? As h goes to 0.
0.
It does. It better. Otherwise, we do have a problem, right? So that if it is the case that you end up getting a number and the denominator is going to 0, then the numerator must go to 0 as well, right? And so that the problem that the denominator is creating by going to 0 is in some sense solved by the numerator going to 0, right? And another way to think about this is that what's the limit as h goes to 0 of h over h? Yes, but wait, I thought we had a problem because the denominator was going to 0, right? So just because the denominator is going to 0, that's not the end of the world as long as the numerator goes to 0 how? At the same rate, right? As long as they go to 0 at the same rate, then things balance out, and this is 1. So actually, we're making a remark about this. We're saying that e to the h minus 1 around 0 behaves very much like h, right? We're saying that they're very, very similar, right? That is an excellent question, right? And so that happens a lot, right? Where it seems like there are problems, but this is what happens in infinitesimal calculus, where things are getting really, really small, but things are balancing out. Right? That's a good question. All right, other questions about this? The derivative of e to the x is e to the x. Okay. We said the product rule, the derivative of f g is f prime g plus
G prime.
g prime f. This should help us actually find the derivative of e to the 2x. E to the 2x is actually just e to the x times e to the x, right? I could call that f, call that g. F prime is e to the x. G prime is
E to the x.
e to the x. The product rule says that f times g prime is f prime g plus g prime f. Well, it's f prime g plus g prime f. That would be e to the x times e to the x plus e to the x times e to the x. That's e to the 2x plus e to the 2x, which is 2e to the 2x. We might be getting a visit from the overbearing student in a moment. She's here. She says, oh, that's nice. What's the derivative of e to the 3x? 3 to the 3x, it would seem, right? So we'll do this one more time for her. The derivative of e to the 3x, what is that? It's the derivative of what nice thing? How can I write this as a product? What times what?
E to the x.
Times? Absolutely. Oh my God, I love intelligent people. E to the x times e to the 2x. I now know the derivative of both of these, right? So if this is f, so this is called an inductive argument. And so f prime in this case is e to the x. We just showed that g prime is
2e to the 2x.
2e to the 2x. That's what we just did over here. The product rule says the derivative of fg is f prime g plus g prime f. F prime is e to the x. G is e to the 2x, right? G prime is 2e to the 2x, and f is e to the 2x. I'm sorry, e to the x. So this is equal to e to the 3x plus 2e to the 3x, which is 3e to the 3x. Please.
Why is G prime e to the 2x?
Thank you. That's a great question. So here is e to the 2x here, right? I'm going to take a derivative of it. I used the product rule, and all of that work gave me this. So the derivative of e to the 2x is 2e to the 2x. Is that okay? So that when I come down here and I have e to the 2x, what's the derivative of this? That's why I wrote it. That's right. Excellent. That's why I have it here. Good. Now the great skeptic comes in. Well, I'm sorry, I haven't even made the remark. It looks like that in general, if h of x equals e to the lambda, I'm sorry, I don't want to introduce new Greek letters, alpha, let's do e to the ax, then the derivative is what? ae to the ax. It's just like the number comes in front. Now, of course, the great skeptic comes in and says, you only did that for two numbers. And you want me to believe that? And that's reasonable, right? So I'll have to give a deeper proof for why this is true. Again, this is by induction. You can do this by induction for integers. That is to say that notice how, here's the argument. Notice how the first one, the derivative of e to the 2x, right, is 2e to the 2x. But the derivative of e to the 3x, I used e to the 2x, right? So because the derivative of e to the 2x worked out, the derivative of e to the 3x worked out. And if I want to do the derivative of e to the 4x, then it relies on the derivative of e to the 3x. Right? And that works for any integer. So that because we have a statement about the natural numbers that works for one, and then if it works for one, it works for the next, then it works for all of them. Right? That's called induction. So that's definitely a study session type discussion that I'm willing to talk about for my math majors in the house. Okay, great. So we're going to take this for granted, that the derivative of e to the ax is ae to the ax. And that's going to be true for any real number, although I made an argument for natural numbers. So in general, the derivative of e to the minus 2x is e to the minus 2x times negative 2. Right, so you just bring the number in front. Okay. Questions about this, about the exponential function? Now, the exponential function, we say it grows really quickly, right? So exponential functions have the property that, again, e is bigger than 2. I mean, 2 to the x on its own is already big enough, right? At 10, 2 to the x is already 1,000. So at 20, it's a million. It's over a million, right? This crushes any function that we talked about. This crushes every polynomial, right? Basically, that we talked about. That exponential functions get big so quickly. So it's almost like, in terms of its rate, it's almost like it perpetuates itself, how big it gets, right? So when we look at how big this gets, and we zoom out, we can use a little bit of calculus to see why this makes sense. That if the derivative, if this thing's already big and then its derivative is itself, then you can see why it continues to get bigger and bigger the farther we go. Because if it gets bigger and bigger the farther we go, and its derivative and the rate at which it's changing is the same thing as how big it is at the time, right? That this thing's huge at this point, but then its derivative is the same value as how big it is, right? So the bigger it gets, the faster it increases. Whew, my goodness. The bigger it gets, the faster it increases, right? That's crazy fast, right? And of course, we haven't even started, right? Of course, I could talk about 10 to the x, 30 to the x, like outrageously large functions, x to the x, right? So, yeah, that gives you an indication, a calculus reasoning for why the exponential function is huge, right? Show using calculus that the exponential is increasing. Why is the exponential function increasing? So this is going to rely on something we haven't shown yet, but we have some indication. So if f of x is equal to e to the x, we're going to show later, then if I want to show f is increasing, what do I want to say about its derivative? Positive. Well, what's the derivative of f prime? What's the derivative of f? Which is positive. I have a function whose derivative is positive, so that makes it automatically increasing. It increases on the whole row line, and its derivative increases without bound. Okay. Okay, excellent. We now have a different function. Now we can apply all these other rules, right? So h of x is equal to x squared e to the x. What's the derivative? Take the derivative of that. So now we're going to start implementing some of these rules. You look at a function, you say, well, wait, what rule should I use to do this? We have a product rule that says if I have one function times another, then I can use this product rule. You make f equal to x squared, g equal to e to the x, and use the formula. We'll do some applications as well today. Talk about the quotient rule. Please.
Oh, do you have any preferences to how we simplify?
No, so yeah, not on the test. No, so yeah, I'll be instructing Jessica and having a personal conversation with myself as we grade about, yeah, we're expecting multiple ways of getting to the answer. And we're going to respect all of those ways if they're right. We're going to respect all answers, but you're only getting points if they're right. Right? We respect all answers. So, yeah. So, but I will detail as I do this one how this would be graded. For example, yeah. F in this case is x squared, or you could. I'm going to assign f to x squared, so I'm going to call this f. This is g. The derivative of fg is f prime g plus g prime f. F prime is, what's the derivative of x squared?
2x.
2x. The derivative of g?
E to the x.
E to the x. And what I want to say is that, again, for my people who have never seen this stuff before, I would imagine, and I could be wrong, but I would imagine that it might seem like we're going fast. Right? We had just introduced polynomials and the power rule yesterday, and I just act like it's secondhand knowledge, like you know it like the back of your hand. That is the standard for trying to do a Calc 1 course in 5 weeks. I mean, you meet every day and we just go, right? So it does require. This is kind of part of the reason why this homework, very frequently, because you got to get the practice in, and we're just going to go. Right. So again, this is why Jessica is here, and this is why you're going to have a TA at whatever college you choose, right? Because the speed is, thankfully, in college you only meet twice a week or something like that during a regular semester. But summer classes are just crazy in that way. Okay. F prime g plus g prime f. So if you are struggling, please let me know. F prime is 2x times g e to the x plus g prime
E to the x.
e to the x times f
X squared.
x squared. This is 2x e to the x plus x squared e to the x. So yeah, I mean, we'll take that. This is probably what is fine. I would take this on the test. I have not tested out the homework system enough to know which one it would like or prefer. I would imagine it would take either one. But yeah, again, this is good enough only because I'm simply testing on the rule. And if I see this, I know that you know the rule, right? Questions about this, how it would be graded? Let's go ahead and do f of x equal to, let's do x e to the minus x. That's it. Just x e to the minus x. Find the derivative of that. Oh, please.
On the test, do you want us to write it with like fractions and negatives, or would you rather us simplify it?
Oh, that doesn't really matter to me. The simplifying. So see, if you have negative exponents, I'm perfectly okay with negative exponents. I don't have any phobias about things like that, right? X to the minus 2 is 1 over x squared. We know that. You can write it as x to the minus 2. The programmer, though, I think for the homework system wants positive exponents, right? So. The derivative of uv is u prime v plus v prime u. And I'll probably use that, and I changed letters because I've already called this f. And this is good notation for the integration by parts anyway. So the integration by parts formula, next year, right, is derived from this formula here. It's just the inverse of the product rule. If this is u, that's v, u prime, the derivative of x, 1. The derivative of e to the minus x times negative 1. Right, so the coefficient of x in this case is negative 1. And so the negative 1 comes out in front. The product rule then says u prime v plus v prime u. U prime is 1 times v is e to the x plus v prime is a minus e to the minus x, and then u is x, rewriting this, e to the x minus x e to the x. And that's the derivative. It is, thank you. Questions about that? Please.
For the u prime, why didn't you keep that? Why did you just put 1?
Why is it 1? Excellent, thank you. So if u is equal to x, so when I write u prime, I'm asking about what does u prime mean? U prime means so this is good. So when I write prime, I mean take the derivative of x. So what's the derivative? What's the derivative? It is. That's right. What's the slope of y equals x? Yes. Is that okay? Okay. All right. So this is good. I'm going to be good. I'm going to be harder on you in a loving way, faster. All right. So you're not reading your notes, whatever it is, right? That's supposed to be way quicker than that. Okay. So I'm gonna hold you to a high standard because we're gonna move fast. Okay. So good. I appreciate your question, and so keep asking them. But that's 1. Yeah, so the derivative of x is 1 because it's the slope, right? And it also follows from the power rule, right? That it's x to the first, and so you bring the 1 in front. It's 1x to the 0, and x to the 0 is 1 for any non-zero number. Okay. Okay, excellent. So, tell me about this graph, x e to the minus x. We know what x looks like. Looks like that, right? E to the minus x, what does that look like? Like this, right? Okay, so that's x. Here's e to the minus x. What happens when you multiply? What happens when you multiply? We'll graph it, of course, in a second. What happens around the origin? What does it look like around here? Okay, so good. So what happens when x is really small? What happens to this when x is close to 0? What does this look like? It looks like 1, right? So all I'm asking is what's the limit as x goes to 0, right? And that's e to the 0, which is 1. Yes? Okay. So that x e to the minus x around 0 looks a lot like what? If this looks like 1, then the whole thing's going to look like...
0.
Look, yeah, it's going to look like 0, but how do you get to 0? Looking like what function? X. Yeah. So it looks like x around here. Okay. Is that okay? Looks like x. And then when x gets large, when x gets larger and larger, what happens to x? It's doing like this, right? What happens to e to the x? E to the minus x. It looks like this, right? How does this resolve itself? X is going all the way up like this. It's like a fight. X is getting larger and larger and larger. E to the minus x is getting smaller and smaller and smaller. Which one wins?
E to the negative x.
E to the negative x wins. That's right. We had made the argument that e to the x grows way faster than x, and therefore e to the minus x should decay much faster than x grows for the same reason. We'll prove all of this stuff later. Right? What does that mean? That means that eventually, that early on this looks like x, but then e to the minus x will bring it down. Right? It says, yo, you might be getting big, but I'm getting smaller faster than you're getting big. Okay. What happens all the way to the left? Well, e to the minus x flies up to infinity on the left, but x on this side is always what?
Getting smaller.
Not getting smaller, but what's the sign? It's negative, and therefore I have something going to infinity, but in a negative way. It looks like that. Okay. Let's go ahead and graph it formally. Oh, how convenient. Need to change the exponent. Make that e to the minus x. Let's zoom out a little bit. So we can make this argument. There's e to the minus x, and then we'll put an x in front of it. And there it is. Let's see about that. Now, oh good, I get to be old now. That back in my day, we didn't have Desmos, you know. One of these things that with this just stunningly beautiful software that just gives us this picture, you know. Just 7 years ago, people just had to deal with my shitty ass picture, you know, that I just drew. That was the best they had, right? They may have had a TI-84 or whatever, right? But yeah, this is remarkable, right? So it's obvious here that the maximum is 1, and that it's at 1, and that's the maximum for the whole real line. Right? But again, if you can just step out and imagine a time in which this was not presented to us, how we would show that this is the maximum value. The maximum value is at 1 on the whole real line. X e to the minus x is defined for every x on the whole real line. And I claim that no matter what number you plug into x e to the minus x, it's always less than the number you get when you plug in 1. How amazing is that? That's unbelievable. Out of the infinitely many numbers on the real line, the maximum is at 1. Right? That's what we want to show. Right? Now, we could be automatons and just look at the graph and say, "What was it? Look! Right? Can't you see that? Right? How would you do this without the picture? Right? That's the question. So we would need to. And what does this have to do with calculus finding the maximum? Go ahead.
Yeah. Well, it's when like the slope goes from positive to negative.
So go ahead.
The derivative goes from positive to negative, like
So we're talking. So this is good. So we're talking about the function, right? So let's just talk through this. There's the function f, and now you start mentioning derivatives. But if we're talking about f, let's talk about, no, yes, we do, but let's talk about f first. So if someone on the street comes to you and says, well, wait, how do you know this is the maximum? All we want to say is, yo, here's the deal. Can I convince you that this is the maximum by arguing that f is increasing before this and then decreasing after this and never coming back up? And then everybody agrees with that, right? That this is the maximum because you would be convinced that this is the maximum if I could show you that f is increasing before this point forever and then decreasing after this point forever. Yeah? That's obviously a question about derivatives. So that if we can show that the derivative before this point is is positive, and then the derivative after this point is negative, then this is the highest point. And that's what we would have to show. That's what you were trying to say. Okay, exactly. Very well done. So, we have the derivative. There it is. What's special about 1? What's the derivative here? 0. Let's show that. We have the derivative. So if we want to find where the derivative is 0, so f of x is equal to, f prime of x. Did I call it f? I think I did, right? So f prime of x is e to the minus x e to the minus x. That's the derivative. I'm going to set that equal to 0. There's a reason for that I need to explain why we're setting that equal to 0. Here we need a little bit of algebra. I notice that both of these have what in common?
E to the negative.
Factor it out. 1 minus x is equal to 0. This means that one of two things. This means that e to the minus x is 0, or it means that 1 minus x is 0. And we know that the exponential is never, this is never true, and therefore the derivative is 0 at 1. Is that okay? Questions about that? And so now, what people may have done is then an analysis of this derivative. F prime of x is equal to e to the minus x times 1 minus x. The exponential function, we didn't say this yet, but the exponential function is continuous. You look at the graph, no jumps, no breaks. To show that's pretty difficult, but hopefully it's clear that you can draw the exponential without taking your marker off the board. When you look at the derivative, now we need to make an argument that what's the derivative over here? Positive or negative? How do you know? Oh, you pick a number? Pick a number bigger than 1? Okay. Give me a number.
2.
2? Okay. And then do what with this number? Plug it in. F prime of 2 is e to the minus 2 times 1 minus 2. That is negative e to the minus 2, which is that positive or negative?
Negative.
That's negative, right? Because the exponential is positive, but a minus sign in front of it is negative. And so what does that mean? That means what? Because the derivative is negative?
Yes.
The derivative is negative everywhere past 1? Yes? Okay. Now, the great skeptic has come in, right, and is waiting. But we'll make another remark about over here. And over here, what happens? You want to pick what?
0.
Pick x equals 0. Plug in 0 into this. F prime of 0 is e to the 0 times 1 minus 0. That's 1, which is positive. So you pick 0, and the derivative is positive at 0. So it's increasing at 0. So now you want to tell me it's increasing everywhere before 1 because it's increasing at 0? Oh, wait, what? Now you've left me?
The derivative is increasing at 0 because it's positive. Because the derivative is positive at 0, the function is increasing before 1.
Say that one more time.
I said because the derivative is positive at 0, the function is increasing
At 0.
at 0.
At 0. But is it increasing at -5?
Yes.
Well, you just go in and check it.
So.
Yeah, we can go in and check that. Right, but the skeptic clearly, you picked one value, and now you want to tell me about the whole interval. You see why that's strange? You pick one value, and now obviously there's a reason. You're right. I just need to know why that is. Go ahead.
I think because when you set the derivative equal to 0, you only get one critical number, which is your y.
Yeah.
So you don't have any other so there's no other numbers left. So no, 1 is the only critical numbers surrounding 1 are the only numbers you need to check for because 1 is the only critical number.
This is good. No, this is exactly what education is, right? You finding the words to articulate what you know inside is true. Give me one moment. So that, I've been thinking about this a lot, about what education means, right? And that I know a ton of people who are brilliant but cannot articulate what needs to be said so that anybody understands them. And oh my God, I love those people. But then you have to ask yourself, where do they stand on the pantheon of educated people? If what you have in your head, you can't get out to anybody else in the world. That just makes you a recluse, right? Right? So that education and getting an education is partly about making that very struggle, right? To within you know what the answer is, understand something about this life and about this world, and then to be able to articulate it to people so that you transform them, right? So, okay. So I think I get what you're saying. Other explanations? Go ahead.
Because we set the derivative equal to 0 before we factored it, the slope of a function relative to 0, either when it's changing direction, like in a parabola, is the slope of 0 is at its maximum, which means that the derivative is increasing on the way up. Oh, if it's a negative, increasing on the way up and decreasing on the way down.
Okay.
So because we set it equal to 0, that means it is only the only critical number that we need to solve for both sides.
Okay, so everyone's saying something similar. Okay, that's okay. Okay, I hear that. Other comments you want to make about this? So I can try and translate what I think I'm hearing. Go ahead.
I mean, it works for this one because there's only one solution.
What's there's only one solution? You mean x equals 1?
Yeah.
Okay, go ahead.
So
and
if
therefore,
there are multiple solutions, then the function could have multiple minimum maximums.
that's true.
So you can't assume that if it has multiple.
So you're saying it has to do with the fact that it's the only one. Okay.
Well,
So good.
Even if there is multiple, you could still go in and check each point, go to the left and the right to determine whether it is increasing or decreasing.
Right. Okay, so good. I've heard tons of great things. And I don't know if I've gotten the exact answer to what the skeptic is concerned about. That you told me that you put in 2 to the derivative, got a negative number for 2, and that means I'm sure that when I put in 10, I'm still going to get a negative number. Right? When I put in 452.328, I'm going to get a negative number for the derivative, right? And so I think I may have heard why that's true. And it has to do with 1 being the only one, right? So the great skeptic has come in, and yeah, we're going to have to fight her. She says, well, we know how to fight her now, right? Now we're going to make our claim as crazy as it is, and she's going to respond to us. Yo, what are you trying to pull over on us, right? On me, right? You plugged in 2, got a negative number for the derivative, and now you want to say that the derivative is negative the whole way, right? And then, of course, and you say yes, and then she says, I don't believe you, right? She says, I don't believe you. And then what must that mean if she doesn't believe us? That if it's not negative the whole way, then it has to be positive somewhere else. And so you say, well, if you don't believe it's always negative, that must mean that you think it's 0 or positive somewhere else. And then she says, maybe it is. And then you say, okay, well, so it's under the x-axis before 1, and we're talking about the derivative. So after 1, it's under the x-axis at 2, and then all of a sudden, you think it hits above the x-axis somewhere else. And she says, maybe. And then you say, that's not possible. And it's not possible. Why not? Because if it's negative here and positive here, what must happen? Why? Why does it have to cross the x-axis? That's the intermediate value theorem. That's the intermediate. Okay. So by the intermediate value theorem, if it was positive somewhere else, then it would have to cross the x-axis again, but that can't happen because indeed that was the only place where it was 0. Okay? So that's why you're able to only pick one point, and that point speaks for the whole interval. Right? Not just because we said so, right? Because of the intermediate value theorem, because e to the x is continuous, e to the minus x is continuous. Okay? Questions about that? To your point earlier, there's only one critical number, whatever that means. There's only one place where the derivative is 0, and so that actually does mean something for continuous things. And so the way that we would say it would be to say, look, this is nice and continuous. There's only one place where the derivative is flat, and so this is what everyone was trying to say basically. That means that because everything is nice and smooth, then if this is the only place where you're flat, then everywhere else you're either going up or down. But you can't, if you're smooth, you can't go up again without being flat again. Right? So I can't, if I dared to try and go back above this number, right? So the argument goes, this is the maximum, because what would happen if this wasn't the maximum? Say it again? That's right. Right? So if the skeptic comes in and says, yo, I don't believe this is the maximum, then you just say, well, okay. He says, I don't think this is the maximum. And then we just say, oh, you don't? And then he says, no, I do not. And then you say, well, that must mean that you think that somewhere else it's higher. And we just did this with the derivative, but let's do it with the function. And then you say, well, and then they say yes. I'll say, well, this is smooth. And then he says, yes. And so that means you must believe it does something like this. And then he says, yes. And then you'll say, well, that's a problem. Because that means, what about this point? The derivative is 0. But this was the only place where that was the case. Right? So if you only have one critical number, if you only have one place where the derivative is 0 for a smooth function, that place has to be the maximum or the minimum. That's a true statement. One critical number gives you the maximum or the minimum for a continuous smooth function. Okay. Questions about that? Okay, excellent. Another application, f of x equal to x squared minus 4x plus 3. Where's the vertex? Oh, you remember our pre-calculus?
Negative 2. No, 2.
How'd you get that?
Negative b over 2a.
Negative b over 2a. So a is 1, b is negative 4, c is 3. We learned in algebra that the vertex is at x equals negative b over 2a. In this case, that would be negative 4 over 2 times 2. 2 times 1, thank you, over 2a. Negative 4 is 4 over 2. The vertex, the x-coordinate of the vertex, is at 2. And to get the y-coordinate, you will plug in the 2. Remember that stuff? Okay, excellent. Let's go ahead and derive this formula. So if I want to prove that this is where the vertex is. So given a quadratic function, this is quadratic because it's a polynomial of degree 2. Given a quadratic function, I want to show that the vertex is at negative b over 2a. How would you do that? Look at what generic function? F of x equals ax squared plus bx plus c. Right, so now the genius of this thing right here is that you can actually put that in. Just so sick. Right. Ax, and then slide everything, right? Ax squared plus bx plus c. And slide it all. I'll be x plus c, right? So let's zoom out. And then we can move A, B, and C, right? So B has something to do with the vertex, right? Oh my goodness. That is ridiculous, right? That is absolutely outrageous. Because what it's saying is, what is it saying about how the vertex depends upon B? What does it look like? It moves along a what? It moves along a parabola itself. That the position of the vertex, depending upon B, looks like it's a parabola, right? I did not know that, right? C, of course, should just affect how far up and down it goes, right? Go ahead.
In terms of, you said before that we use the generic formula to find the, is it
Yeah.
better to use the generic formula to find the
X-coordinate of the vertex.
Yes.
Yeah.
Can we typically use the derivative in order to find this with the generic formula?
That's correct. That's what we're about to do. Yeah. A, of course, affects how it opens.
Negative is positive.
That's right. When it's 0, it's not quadratic, right? So we don't want A to be 0 for that reason. Otherwise, it wouldn't be quadratic, right? And then, okay, great. So we want to show that the vertex is always at negative b over 2a. Now, it so happens that the vertex is the place where the derivative is equal to 0. So we're going to take the derivative and set it equal to 0. F prime of x is equal to a times the derivative of x squared, 2x. The derivative of x, the derivative of c. What's the derivative of c? 0. Two ax plus b is equal to 0. We're solving for x. 2ax equals negative b, and x is equal to negative b over 2a. The great skeptic just whispers, well, wait, how do you know you're not dividing by 0? A can't be 0. We said that in the beginning. So, there it is. So again, there is the formula. We just say it in algebra, but the calculus makes it very clear why that's true. Okay. The vertex is at negative b over 2a. Okay, excellent. The quotient rule. We can do this in a couple of ways. We could use the definition, or we could use the product rule. Let's try and use the product rule here. So the first thing I want to do is I want to do the derivative of 1 over g of x. What's the derivative of 1 over g? Negative 1 over g squared. Is that it? Okay. All right, so let's look. I don't think the units are right. So how do I know that the units aren't right? How do you know the units aren't right? So what g is just a function, right? What is m? What is m prime? M prime is a what? Begins with an r. It's a rate. G is not a rate. M prime is a rate. I have a rate that's equal to not a rate. What am I missing? I'm missing a rate. Right? I mean, yeah, so again, yeah, you just can't write this without a rate, right? So it has to be times the rate. And so, and again, you can check. Not now. You can check by putting in, if you want x to be in time and m to be in feet, this is in feet per second. And if you didn't have this, if g was in feet, this is just 1 over feet squared, right? And so this is feet per second, and then that's 1 over feet squared. And so, yeah, we'll need to look at the units very carefully for this one. But yeah, so if you have a derivative on this side, you got to have a derivative on this side. Right? We'll say it that way. Okay. Let's prove that. M prime of x is equal to the limit as h tends to 0 of m of x plus h minus m of x all over h. This is equal to the limit as h tends to 0 of m of x plus h is
1 over g of x plus h.
1 over g of x plus h minus
1 over g.
1 over g of x all over h. Perfect. So here we are again with this complex fraction. Okay. This is equal to the limit as h tends to 0. Let's just remember where we're trying to get. We want to get minus 1 over g squared times g prime. Say it again. You can. Absolutely. So she wants to introduce this new thing. I was going to find a common denominator, but I want to be fair to all the ways to do things. She wants to do this and say times g of x plus h all over g of x plus h. Right?
I like that, just the numerator.
You want to multiply a number by a fraction by just the numerator and keep the fraction the same?
As in, like, take that numerator, like the 1 over g times x plus h
Yeah.
minus 1 over g x, and just simplify the top.
By doing what? I'm sorry.
She wanted to find the common denominator.
Oh, so you did want to find the common
Yeah.
denominator. Oh, okay. I thought you wanted to do
Oh, no,
this.
not like that.
Oh, okay. Some people like to do it that way. But you wanted to do that? No, some people like to do it. See, she likes to do it that way. So you don't like finding the common denominator.
I don't like fractions.
Yeah, right. No, neither do I. I usually do it the way that I just did it, but people like fractions too, so bear with us. This is the limit as h tends to 0 of, okay, common denominator is g of x plus h. We'll leave this h down here. And then this needs a g of x minus g of x plus h. This is equal to the limit as h tends to 0 of, we got a ton of rearranging to do. This is the same as 1 over g of x times g of x plus h times g of x minus g of x plus h all over h. You see that those are the same? Okay, let's fill in some steps to that. This is equal to the limit as h tends to 0 of, everyone see we can put this h here? G of x minus g of x plus h all over g of x plus h, right? Divided, yeah, times 1 over h is divided by h, right? Which is equal to the limit as h tends to 0 of g of x minus g of x plus h all over g of x times g of x plus h times 1 over h. Right? Because when you divide by a number, it's the same as multiplying by its reciprocal. And so then I get to rearrange these things however I want because I'm multiplying. So then I can just switch the order of these. So this is g of x minus g of x plus h over h times 1 over g of x times g of x plus h, because it's just multiplying. Right, so I just switched the order. The final remark is that this is equal to, or one of the final remarks, this is equal to the limit as h goes to 0, and then this order is probably backwards for what I intend to be doing. So this is minus g of x plus h minus g of x all over h times 1 over g of x times g of x plus h. And now I'm ready. Apply the limit. What does this thing go to as h goes to 0? That's g prime. That's right. So negative g prime. And as h goes to 0, what does g of x plus h go to? G of x times another g of x. That's what we wanted to show. So the derivative of 1 over g is 1 over g squared, negative 1 over g squared times g prime. Negative 1 over g squared times g prime. We're rarely going to use that rule. Oh, go ahead.
I still don't understand why you substituted the second. The 1 over g.
I'm sorry, where? Here?
When?
Here? I'm sorry,
Oh,
yeah.
yeah, I don't understand.
How this became g of x? Thank you. So g of x plus h, as h goes to 0, right? So as h goes to 0, this h disappears. And it's just g of x. Yeah. Yeah. So yeah, this goes to g of x plus 0, which is g of x. Excellent. And that's only because g is continuous, right? And you can just plug in the number. So I won't use this formula on its own a lot. I brought this formula up because it helps with the quotient rule, right? So that now, when I have the derivative, let's call it q. So when I have q of x is equal to f of x over g of x, like that, right? We can now prove the quotient rule by using the product rule, because this is f of x times what? 1 over g. And so now when I take a derivative, I can prove this. Now, usually in the past, I've used the definition to do this. This is the first time I've actually done this using the product rule. But, I mean, using the definition, I may want to offer that as extra credit, because when we did the derivative, when we did the product rule, we did this magic thing. We added f of x plus h, g of x, subtracted the same thing, right? And then magic happened. And for the quotient rule, using the definition, you do something similar. So I may want to offer that for extra credit. How would you prove the quotient rule using the definition instead of doing it this way? But here's the claim. I'm sorry, go ahead. Yeah, you turn it in on the day of the test. Yeah, so the day of the test, you turn it in with your test, and then I can just add the points on top of the test. No, it won't be on the test. Yeah. So I've given one so far, right? One extra credit, and I'll write out the extra credit. Remind me to write out the extra credit after we do this. Anyone?
Show that f is decreasing.
Yeah. So when if f is a decreasing function, then the derivative is negative. Yeah. Quotient rule. And once I share this with you, get a link to this document, you'll be able to go through and find it, right? So q prime of x is equal to quotient rule. What in the world? Okay. So feel free to use the notation I have here. G times f prime
Minus f g prime over g times g.
G times G. Interesting. I never heard that. Okay, great. Okay, so that's good. Right. All right, good. So I hope. So that's what we want to show. This is a claim, right? So that's a claim. So if Q is that, then Q prime is G F prime minus F G prime all over G squared. Now, from the definition, it's hard to see where this G squared comes from, but now, hopefully, it's not so hard to see from the way we've done it before, that if the derivative of 1 over G is minus 1 over G squared times G prime, then it's clear to see where this G squared comes from in the denominator, right? So I may just do it this way from now on. Okay, so that's what we need to prove. Here's the proof. The derivative of Q is the derivative of f of x over g of x. And so this is our first proof of a derivative without using the definition. We're going to use the product rule. This is equal to the derivative of f times 1 over g. And now we're going to invoke the product rule. U in this case is f, v is 1 over g, u prime is f prime, v prime is
G prime x times 1 over g x squared.
perfect. Right. U prime is f prime, v prime is minus 1 over g squared times g prime. And now by the product rule, we're supposed to have u prime v plus v prime u. And that needs to turn out, we might need to do some simplification, but that should give us the rule that we have. Okay. So u prime is f prime. V is 1 over g, yes? So we're just matching up. V prime is this ugly thing, minus 1 over g squared times g prime, right? That's all v prime. And then u is, was u just f? F. Okay. So u prime is f prime, v is 1 over g, v prime is all of that, and then u is just f. And the question is that f prime g minus g prime f all over g squared? Right? We just need to find a common denominator. Right? So to finish this off, I'm sorry, questions about this?
How do you get the g that out of the denominator into the numerator?
Oh, because I think we're going to find a common denominator. The common denominator is g squared. And so this is missing a g.
Okay.
Yeah. And so that's exactly how we're going to finish this off. So then now, let me just write this carefully. It's f prime over g minus g prime f all over g squared. And the common denominator is g squared. And that is where you get the extra g, f prime g minus g prime f. I put g f prime.
You put g, because this fraction should be the opposite, because before you wrote g prime f of x times f prime g of x.
Well, they're the same, right? This is equal to g f prime. So okay, so good. So we have f prime g, right? Is that okay? Is that the same as g f prime?
No, I meant like in terms of subtraction.
Okay.
Because before you wrote f prime g minus g prime. I'm sorry, before you wrote g prime f minus f prime g.
Minus
but now
f.
we're doing f prime g minus g.
Oh, I didn't write f prime g. Then I write g f prime.
You wrote g prime f.
Oh, let's take a look. This says g f prime.
Oh. Okay.
Is that okay?
Yeah.
Yeah. So we have f prime g minus g prime f, which is the same as g f prime minus f g prime all over g squared, right? So it doesn't matter how you write these in order because you're just multiplying. Right? So that is the quotient rule. Questions about this? About how we get there? Please.
You went from the orange part to the.
I went from the orange part here, right? So I just asked the question, well, wait, this is where we wanted to get. Are we sure that where we are now can take us here? And the answer is yes. And the way that we get there is by doing this. Right? It's to say that, oh, let me rewrite this. This is just the difference of two fractions. And where we wanted to get looks like one whole fraction. And so obviously, in order to make two fractions one fraction, we find a common denominator. Questions about this? So we're into, obviously, again, what we're doing is building tools so that we can ask about as many functions as possible what the derivative is, right? That's the point. So that any function you can think of might be, so when scientists are rolling around in this world, all sorts of functions come up in terms of the applications you have. Again, for biologists, it's the exponential function I was mentioned the other day. For economists, it's other functions, lots of polynomials. For other functions, it might be rational functions. For certain scientists, the ratio of two polynomials is really important. Clearly, we might want to know the derivative of that, right? And now we can do it, right? So the product rule, the quotient rule, the chain rule, all of these things that we're going to introduce are so that we can take derivatives of all of these functions. Given that I just mentioned rational functions, they are now in our wheelhouse to take the derivative of x squared minus 4x plus 3 over 15x to the third plus 5. What is the derivative of that? We're going to let, so now when you see the ratio of two functions, you immediately think quotient rule, right? Quotient rule. Make the numerator one function, make the denominator another function, and just use the formula, right? Alright, so f is the numerator, g is the denominator. We'll calculate f prime and g prime, and then we'll just do g f prime minus f g prime all over g squared. It is here where simplification is a pain. Again, I will go through this problem after you finish it. I will go through it to make clear to you how this would be graded by Jessica and I. But in terms of the homework platform, you're probably going to have to simplify to a point where it likes it, which is a pain, whatever that means. So I am expecting some of you all to say, I have written it right, but it didn't take my answer. That might be possible when the programmer wants this particular answer and you have something equivalent that she did not just program into it, right? You understand what I'm saying? Yeah, so if you've done something right and your answer is equivalent, but the homework system was just like, no, that's not what I wanted, then we'll just let Jessica know and she'll correct it. She'll give you credit for it. I'm going to get started. F, that's G. F prime, the derivative of F is 2x minus 4. The derivative of G is 45x squared plus nothing. And that is fast. Again, that is fast for my people who have never seen calc before, right? That gotta practice. Someone mentioned this to me before, but yes, the book is available and it has practice problems. You can practice in there too. The derivative of Q is f prime G minus G prime F all over G squared. We got everything. 2x minus 4 times x squared minus 4x plus 3 minus G prime is 45x squared times F. I'm sorry, it's 15x plus x cubed plus 3, right?
Yeah.
Yeah. So it's 15x cubed plus 5. This here is x squared minus 4x plus 3 all over g squared. 15x to the third plus 5 squared. And so it is here where if it's on a test, I will take that perfectly with no issue. That's the answer. And people sound happy about that. And so, because now why is this? It's because if I see this, then I know that you know the quotient rule. This is a question just about, do you know the quotient rule? And if I see that, if Jessica sees that, it's clear you know you can't write that without knowing the quotient rule, right? The homework system, though, wants you to multiply everything out, maybe. You should try this first. Try this first, see if it likes it. And if it doesn't, okay. But then otherwise, you're going to need to simplify the numerator out, right? Which is not a problem. Okay. We'll end there. Next time we will we'll do some more stuff with the quotient rule, and we'll move forward. Homework due Friday at 8. I may move that to Friday at midnight. I'm sorry, 11:59. Friday at 11:59. Particularly if you want me to, I will do that. But nobody's doing calculus Friday evening anyway. Yeah. Oh, I know. No, of course not. Yeah.